The source turns seawater into potable water using only solar energy. It's the world's first efficient solar desalination solution suitable for quick deployment.
What if the ocean could give us drinking water, non-stop power, and zero waste all at once? Sounds like a sci-fi pitch, but it's also the dream of every dry city on Earth. Most desalination plants solve one problem and create another. A toxic, hypersaline brine that gets dumped back into the sea. Now, an Australian blueprint claims to erase that waste. It says, sunlight boils seawater. The steam makes electricity. The steam turns into fresh water, and the leftover brine becomes salt. Today, we test the story, the numbers, and the physics. If it works, everything changes fast. Why brine is the real villain? Desalination sounds like a salt problem, but it's mostly an energy problem. Separating salt from water is like unmixing cream from coffee. You can do it, but it takes work. Reverse osmosis uses pressure to push water through membranes. Thermal plants use heat to boil water and recondense it. Both create the same headache at the end. Brine that is saltier than the ocean and often warm, sometimes with added chemicals. Dump enough of that in the wrong place, and local ecosystems can suffer. That is why permits are brutal and slow. A famous example is the Big Poseidon desalination project planned for Huntington Beach, California. It ran into heavy environmental pushback and was rejected by the California Coastal Commission on those grounds. Sol Desal's pitch is basically a fast pass. If you never discharge liquid brine, you can claim zero liquid discharge, or ZLD, and dodge a lot of the hardest arguments. And if the brine becomes a solid product, you do not just remove a liability, you turn a permit risk into a revenue line. That is the emotional core of the blueprint. Don't fight the waste, delete it. And the stakes are not abstract. The UN estimates that billions already live with water stress, and the hottest, sunniest regions often have the least reliable fresh water. That overlap is the Sun Belt, the Middle East, North Africa, parts of Chile, the US Southwest, and much of Australia. Water scarcity also fuels politics. Ethiopia's Grand Ethiopian Renaissance Dam on the Nile has raised tensions with Egypt and Sudan, which depend on downstream flow. So a technology that turns sun into water could cool more than just temperatures. The big claim. Meet the company behind this idea. Sol Desal Australia. Their diagrams read like a magic trick, but the steps are plain. Step 1. Take seawater and use concentrated sunlight to heat it until it boils. The goal is high temperature, high pressure steam. Step 2. Run that steam through a turbine, the same basic machine used in many power plants, to make electricity. Step 3. Cool the steam so it condenses into pure distilled water. That condensed water is the product, not recycled back into the boiler. And step 4. Take the remaining salty brine and send it to a crystallizer so it becomes solid salt, not liquid waste. Only 2 inputs are claimed: seawater and solar energy. 3 outputs are promised: electricity, drinking water, and salt. No emissions, no brine discharge, no out of sight, out of mind ocean dumping. They also say the whole system scales from small remote sites to a 50 megawatt utility plant. It's so neat that your brain wants to nod and move on. But neat diagrams are cheap. Real water and real power are not. So we have to slow down and check what each step costs and what each step breaks. They even say the fuel is free, and the operating input cost is close to zero once the mirrors and tanks are built, which is why they are racing to patent the layout. If that sounds too good, remember, the sun may be free, but steel, pumps, cleaning crews, and maintenance are not. So whenever you hear zero cost, translate it to low fuel cost. Then keep asking questions. The economics they promise. Now for the numbers that make headlines. Sol Desal says their 50 megawatt plant can sell electricity for about $100 per megawatt hour. They frame that as far cheaper than diesel baseload power in remote places, cheaper than coal in some markets, and competitive with renewables. The trick is thermal energy storage. Instead of storing electrons in batteries, they store heat at very high temperatures. They claim the stored heat can sit for days, even months, with losses as low as about 1 degree Celsius per day, and then be dispatched on demand. That turns solar into 24/7 power on paper. On the water side, they project about 1.72 million US gallons per day of fresh water, which is about 6.5 million litres. That could cover around 40,000 people at the global average, or about 20,000 Americans, since the US often uses 80 to 100 gallons per person per day. They also claim a target water price of $1.50 per cubic meter, roughly $6 per 1,000 gallons. In San Diego, typical rates can be closer to $9 to $13 per 1,000 gallons. And in Australia, many reverse osmosis plants land near $3.50 per cubic meter. They even hint they can beat some of the cheapest producers in Saudi Arabia, often quoted at around $2 per cubic meter. It's bold. It's also exactly where hidden assumptions love to hide. The thermodynamics tax nobody can dodge. Here is the part that gets glossed over in many glossy decks. Turning seawater into steam is expensive in energy. Then turning that steam back into liquid water throws a lot of energy away as heat. A normal steam power plant fights hard to recover efficiency. It runs a big condenser, often cooled by river or seawater, to turn steam back into liquid and maintain a strong vacuum at the turbine outlet. Many researchers try to bolt desalination onto a concentrated solar power plant by using the turbine's low-grade waste heat. It sounds smart, but engineers warn it can create back pressure, like kinking an exhaust pipe. That can cut turbine efficiency and push electricity costs up sharply, sometimes by a third. Sol Desal claims to avoid that by using high-quality steam for power first, then condensing it into product water. It is more direct. But ZLD adds its own bite. Evaporating most of the water is one thing. Pulling the last water out of the concentrated brine is another. In simple terms, you might think you only need a little extra energy to remove the last bit, maybe 2,133 joules more. In practice, the last fraction can take around 12,153 joules, almost 6 times more, because solutions behave badly as they concentrate. That extra internal tax can eat into the electricity you hoped to sell. The math can still work, but it cannot be ignored. The salt paradox and the sodium twist. In their model, the brine does not go back to the sea. It goes to a crystallizer and becomes salt. The plant's own figures suggest roughly 165 tons of salt per day, alongside 50 megawatts of power and 6.5 million litres of water. Scale that to a world problem, and you hit a weird wall. The UN says more than 2 billion people live in water-stressed countries. Imagine serving even a quarter of them, say 500 million people. At the blueprint's output, you would need on the order of 3,800 plants. Together, they would also generate a huge amount of round-the-clock electricity, enough to matter global scale. But the salt output would explode too. Roughly 229 million tons of salt each year. Australia is already a top salt exporter at around 12 million tons a year, and the whole sea salt market is around 300 million tons. Add a technology that nearly doubles supply, and salt stops being profit, because commodity markets punish oversupply. So the real value of salt isn't that it sells, the real value is that it is not brine. Still, there is an interesting angle. If sodium-ion batteries grow fast, the world could need far more sodium inputs. Co-locating ZLD desalination with sodium supply chains could turn a waste fix into a materials play. Maybe. But that maybe depends on the physics working first, the one detail that can break the whole plan. Even if you accept the storage, accept the prices, and accept the crystallizer energy, there is a showstopper that keeps coming up. You can't simply boil raw seawater and feed the steam into a turbine as if it were clean. Yes, steam is water. But boiling seawater causes splashing and tiny droplets. Those droplets carry dissolved salt. This is called brine carryover. If salty mist reaches turbine blades, it does two kinds of damage. First, salt particles can erode metal like a slow sandblaster. Second, salt can deposit on the blades and rotor. A multi-ton rotor has to stay perfectly balanced. Deposits create imbalance, vibration, and failure risks that can tear machines apart. Corrosion adds another layer of pain. This is why turbines normally run in a closed loop of treated, demineralized water. It's not tradition, it's survival. So the billion-dollar question is simple. How does Sol Desal create turbine-grade steam from seawater without carryover? The team says they are around technology readiness level 5, meaning lab or pilot demonstration, not a full commercial plant. They have filed for an international patent and are building a minimum viable setup that burns oil first before swapping in solar. That is a sensible path because it tests the hardest part in isolation. But until the carryover problem is proven at scale, this remains a brilliant blueprint with a very sharp cliff edge. So is this the future of desalination? Maybe. The idea is elegant. Sunlight in, seawater in and out comes power, fresh water, and a solid salt stream instead of toxic brine. But elegance is not the same as engineering proof. The energy cost of ZLD is real. Markets can't absorb endless salt, and turbine-grade steam is unforgiving. If Sol Desal can truly stop brine carryover and keep turbines safe, the payoff could be huge for the Sunbelt world. Until then, treat it as a high-potential experiment worth watching, testing, and challenging. Because water scarcity is rising, and waiting is dangerous.